Thank you, Sungmin. Good morning, everyone. Come on. Hey, good morning. Thank you. Okay. It's nice and warm. August came early this week, so sorry, out-of-towners. Okay, so I co-founded Esper Image along with Joe Ed Richter and Jason Trobal, and it will never lead to making money, but here's my financial things. I wanted to start off with the acknowledgments to all the people that, this is some of the people that have been there across my career, both in my lab and Joe's lab, and collaborators and mentors above, peers, younger people that I get to learn from every day. We're like a very technology development focused kind of community, and I think the way that we really push all of the technology forward is by working closely with collaborators that help us optimize both hardware as well as software and analyses towards different application domains, from naturalistic imaging, as was discussed yesterday, for example, in autism or cerebral palsy, to critical care imaging at the bedside and naturalistic environments, for example, during surgery or as kids are in the ICU or undergoing ECMO or heart-lung bypass, but also informatics so that we can push beyond like proof of principle, look what I did with 5 subjects, isn't that great type papers, to actually we had a multi-site study with a couple of hundred people across different continents, and we're showing that this application really opens the door to understanding new physiology, and that requires data sharing that is HIPAA compliant and informatics and computational resources to put it all together. So interacting with all of these people has been really profoundly important. And especially for the younger trainees in the crowd, I think it's really great for summer schools like this that it's not just about listening to all of us drone on up front, but about meeting each other. And I always recommend to my trainees, just make one friend at each conference, and that will grow tremendously over time. And I'm also highlighting in blue one funding source for this conference that was not included with industrial partners last week, but the National Institutes of Health, which hopefully will keep on living a healthy life. If you know, you know. So anyway, part of this is being put on through a U24 mechanism that I want to spend just a moment discussing now. So computational tools for optical brain mapping must address an expanding set of challenges, right? As was discussed yesterday and will be discussed today and tomorrow, there's an expanding set of cap designs with increasing data sizes going from just a couple of fNIRS channels in sparse arrays up to many thousands of measurements in these high-density arrays. And as I mentioned, it also includes challenges in efficient data sharing, cross-modal comparisons, compatibility, standardization of both data type and data flow, as well as ease of use. And so even though the community of software tools has been growing over the last 20 years or so, really none of these tools provide kind of end-to-end processing that we all need to include modeling and analysis and statistical parametric mapping on the brain, et cetera. And so that motivated our development or extension of NeuroDOT, as Joe mentioned yesterday. All of that started when he was a postdoc with David in the early 2000s, but through further development with Brian White when he was a grad student with Joe, who really taught me a lot of what I know when I joined Joe's lab as a postdoc, we started expanding on, let's see if this is going to work. All right, we started expanding on part of what it did. And so what we're building with NeuroDOT are extensible, meaning expandable, MATLAB and Python-based toolboxes for optical neuroimaging. It provides accessible and user-friendly i.e. no Ph.D. required to run. It enables easier collaborations with MDs for processing and analyses, as well as undergrads. Minimal training, ideally, that's what we're working towards. And I can't advance. Hold on. Let's see. No. Oh, that's right. I was told to not do that. Hold on, please. Let's try this button. All right. So we have in NeuroDOT kind of a set of tools that we like to put forth. Rather than saying you have to follow our ecosystem and run everything as if it's an Apple device, ideally It provides just tools that you can use. If you want to use Homer, that's great. If you want to use Atlas Viewer, that's fine. But we also provide a bunch of pipelines for pre-processing, data quality checks, data registration, reconstruction, post-processing, et cetera. MSPay has put up over 400 anonymized and published data samples with tutorials in Jupyter Notebooks for training, and directly supports analyses for any commercial systems. And if you have a commercial system that you feel like is not supported, please let us know and we'll make sure to onboard it there. So I'm sure that many of you have hopefully downloaded this, and we'll learn more about this today and tomorrow. So there's been growing use of NeuroDOT across the world. This is a recent map of some of the IP addresses that we've been able to grab from NITRC. And so coupled with this, we're also deploying OXI for optical imaging, XNAT-enabled informatics to provide global, secure, and HIPAA-compliant optical data sharing. Basically, it follows the BIDS format. You can use any type of data type in the fNIRS or volumetric data type like an fMRI, like NIFTY, 40FP, even DICOM, et cetera, to put your data in here. And the idea is that it provides the infrastructure that you can use to collaborate both within your institute as well as across any of these red dots to just process your data, share your data, analyze your data using standardized routines. And it also offloads the requirement for having the computational infrastructure of your own, or having all of the right MATLAB toolboxes or Python toolboxes or Python versions, et cetera. Everything is kind of standardized right here. All you have to do is log on and you can run everything on the internet. So this was running on WashU-based servers, which means that when the power went out on a hot day, it went down. So we're in the middle of porting it over to Amazon Web Services, and that should be ready in about a month. A central component of the U24 is workshops and summer schools like this one. It's the NINDS, NIMH, and the BRAIN Initiative. Hopefully this will continue for the next 4 years at least. We've been traveling the world to try to meet users to learn what they want tools to be able to analyze in their own worlds, right? So the more we learn about the user base, including all of you and your friends, the more we can make sure that the tools that you need, questions that you have, can be directly addressed in the toolbox, and we can train the trainers in your sites. So this is a list of places that we've been recently, and we're very interested in going to your institute or to your conference or to your lab to just talk to you about our tools and help optimize them for you. Primarily, we focus on brain imaging, but we can also build in anything for fNIRS types of analyses. So please reach out to us if you are interested in helping us put on a workshop. Additionally, training is a central point of this. So we have tutorials for getting started, pad file generation, metadata organization, so the information that comes along with the data that explains how to unpack it, what it means, et cetera, as well as head modeling and array registration, as we'll talk about in a minute, as well as light modeling, pre-processing, image reconstruction on the brain, and then very extensive visualization tools kind of at every stage along this processing. We have been moving from MATLAB into Python-based infrastructure, and so this opens the door to using Jupyter Notebooks, which are a great training resource that allows for inline visualizations and code blocks that can be run in a single click, et cetera. So again, OXI is built on XNAT, so Dan Marcus and the XNAT team have already solved a whole host of problems and challenges for being able to integrate multiple data types, to be able to have HIPAA-compliant data sharing, et cetera. So we're able to stand on the shoulders of those giants to provide our NeuroDOT tools for all of you through these resources. And again, we have Dockerizable containers, some that we've developed, but also we're building in APIs so that you guys can build your own Docker containers, which again allows you or anyone else to just push a button and run a standardized set of analyses, which supports reproducibility, open science, et cetera. You can grab data from our Schrader et al. Paper or one of my papers before and just run your own analyses on it and see what you get. So this is a landing page for OXI with multiple other things, and so stay tuned and feel free to reach out to any member of our team for more information. Again, we follow the BIDS convention, and we have automatic kind of BIDSifying code to put your data in that format, because this is what fMRI uses, the kind of the standard neuroimaging community, and this is something that the fNIRS community has been moving forward to as well. So, with that advertisement over, yes?
How likely are the Montreal and Vancouver workshops?
How likely are the Montreal and Vancouver workshops? That's a great question. So those are currently, we would like to go there, but we just need to find a partner to kind of help us with the logistics, put it on. So if you know someone there, we can make it extremely very likely. I just got back from Italy last week, and I'm still very much in a dream state. So just to say, these are very international, and we're working on, MNIs just across the border, Vancouver, also just across a border a little further away. So I would love to put those on. And if you guys want to travel there, let's do it. So yes, please. All right, learning objectives for this morning. Understand the conceptual steps involved in image reconstruction from data acquisition, image formation. Learn how to use tools such as Monte Carlo, in very brief, NearFaster and NeuroDOT in the reconstruction pipeline, and explore validation strategies for DOT, including comparisons with other references. So just to take a step back and kind of repeat some of what Joe said yesterday, but from a slightly different perspective, we're focused on the brain rather than like the measurement. And so we're always worried about trying to take our measurements and couch them within the brain tissue or the cortical tissue. And so the brain is a very complex system, right? The types of answers you get out of your analyses and out of your data very much depend upon the kinds of questions you're asking. So you can ask questions about task-based responses in the brain, like where in your brain lights up if you tap your fingers, relative to when it's just hanging out, daydreaming, thinking about coffee, or thinking about your grandmother, where in your brain does the grandmother cells start glowing, or task-free approaches, where you can just be doing nothing, or be doing something, but if you're looking at a very low bandwidth, parts of your brains are kind of undulating with each other in ways that if you look at the correlation of how they're undulating, you can actually recapitulate a lot of these resting state networks. And so this was shown in 1995 and has been kind of a cottage industry in fMRI and in fNIRS ever since. So the important thing is that disease, development, aging all manifest as differences in these task-based systems or resting state networks or other types of, again, analytical and stimuli approaches, as Stalin and Kat talked about yesterday. So one of the main challenges that we have as a field is going from image quality that you can get like this in an MRI machine with a large field of view without all the logistical constraints. So you can do studies like Joy was talking about, where two people are sitting next to each other and just naturally interacting, or like we are interacting right now. And so what we've been focusing on in the lab is building systems like this, but now moving towards systems you can apply in the clinic or with Ed, who refused to let me play the audio for this video, but hopefully some of you got to see Ed in front of the ping pong table yesterday wearing one of our systems. So we're gonna go through a few of these topics over the next few minutes. I was trained as a physicist, so at a first approximation, we are, semi-sentient bags of salt water to begin with. And so if you want to measure something inside of the tissue, you have to shoot in radiation and then measure the amount that comes out the other side to a degree. There are four forces of nature. The electromagnetic one is the easy one to use, so we're going to focus on that. The black line here shows the amount of absorption as a function of energy or wavelength or frequency, depending on what school you come from. So low wavelength or long wavelength, low energy is down here. The types of systems that get through biological tissue are like the MRI system. And so we're trying to move away from these big bulky systems that use all the helium that we like in birthday parties. So then at very high energy, you can get through tissue, but it's ionizing, so it's not great for longitudinal imaging in kids. And so in the middle, we have this really nice opportunity called the optical window, where near-infrared light and a little bit of the visible spectrum and the near-infrared wave or the SWIR spectrum is able to penetrate multiple centimeters through biological tissue. But then the challenge, if you recall walking to the workshop yesterday morning, was scattering. So if you shoot a laser through water, it goes straight through, and that's great, kind of like an X-ray. It makes shadows, but it doesn't really diffuse through the body very much. But if we now add blood, it's kind of creepy, but if you add blood, it diffuses around, so it becomes very, very cloudy. And so we have to be able to predict where the light is going to be able to kind of reconstruct or unpack where in the brain was changing its, blushing, as Joe said, relative to our measurements. And so one way, so this is just an example of a pulse of near-infrared light kind of traveling through the brain over a few nanoseconds, video courtesy of Hamid Agani. So kind of traditional fNIRS approaches say, all right, look, you have a source, you have a detector, you look at variations in the time course, and let's say that there's a path length factor of about 6. As you recall, yesterday Joe said it's about 5, so it's in a good ballpark for how long those photons are bouncing around before they go from the source to the detector. But because it's diffuse, unlike X-ray and CT, we cannot simply back project the data into the medium. And so the techniques that we're using, fNIRS, have been broadly used in terms of optical intrinsic signal imaging, as can be used in mice. And then, of course, we're focusing today in humans. But just to say, like, these are the same types of contrasts. So this basic modality, this basic technology can be used across the phylogenetic tree beyond just mice and humans. So big picture, there are kind of 3 broad varieties of diffuse optical measurements. There are more, but just to kind of touch the main, most important bases. If you want to read the mathematical guts, Mariah and I wrote a review paper a few years ago. There are other really great review papers about this, like from Turgut Durduran, 2010, and many, many others. But basically, if you shoot light in, it'll scatter in some direction across a cross-section over an angle. And here's an example from David Boas of a pulse of light coming through. This is a Monte Carlo simulation, basically showing the spatial profile of photons as they decay across time. If you imagine a source here and a detector placed some distance away, the light level you get out looks like this as a function of time and space. And notice that the light level drops precipitously very quickly and decays. And so these time domain systems can be used to take remarkably good high accuracy estimates of absorption and scattering coefficients in the tissue. However, people have not really built high density versions of these, so I'm not going to spend much time on this type of system. There are other systems that build, or the companies that build these frequency domain systems. Dennis is here from ISS, which has, I think, one of the best frequency domain systems you can get. Instead of time domain, what it does is it just shoots the light in as a sinusoid, right? So as the light goes in, you measure the amplitude out some distance away, or the phase, which is just basically the time delay for that sinusoidal wave. And so now you still get 2 types of measurements for any given source detector pair, so you can reconstruct both absorption and scattering. But what we're going to focus on is just the simple dumb approach, which is continuous wave. You shine a light in, and it decays. You vacuum light out, and it kind of decays backwards in time, but it's the same basic idea as Joe talked about yesterday. The fundamental unit of a measurement for fNIRS is a source detector pair. And so you just multiply these 2 Green's functions together, and you get this banana or peanut or whatever you want. But the point is that this is kind of the spatial sampling you have. Hello? This is kind of the spatial sampling you have from a given source detector measurement pair. So you can model all this in any given geometry with kind of any given optical properties using the radiative transport equation. It's really complicated, and it is not solvable in closed form in almost, in the vast majority of geometries that we care about, i.e. your head tissue, okay? So we can talk about what all of these different terms mean. I'm not going to belabor this, and for anything else to say that this is a thing that exists. It was originally formulated as the Boltzmann transport equation in the 40s to talk about nuclear scattering, or neutron scattering in nuclear reactors. But it does a really good job of modeling photons bouncing around in our heads. But it takes a long time to solve this using numerical approaches such as Monte Carlo. So our friend Qingqing Fang and others have their own Monte Carlo packages. MCX and MMC are really beautiful, awesome packages that I highly recommend you check out. You can use the outputs of both of these in NeuroDOT. There's a tutorial in our documentation folder for it. Again, it solves the RTE in any arbitrary geometry. However, it's really slow. Who in the room has ever run a Monte Carlo simulation? Anyone? Okay, wow, a lot of you. That's awesome. It takes a minute, right? So you get really beautiful answers, but it is remarkably slow for a source and detector. So if you have 100 sources or 100 detectors, you're going to have to get a lot of coffee while you wait. And it doesn't really matter if you're doing imaging in humans, even in babies. If there's a lot of CSF, maybe you want to run a Monte Carlo simulation to double check, et cetera, as we'll talk about in a minute. But essentially, if you're not within the first couple of millimeters from the source or the detector, and if you're in the highly scattering regime, which most of our tissue is, again, if there's not a ton of CSF, and you care about differential imaging, the diffusion approximation works remarkably well, like extremely well. And it's very, very fast to calculate, as I'll talk about in a moment. So here's the diffusion approximation written very slightly differently from what Joe showed. You can make approximations to go from the RTE to the diffusion approximation. I'm not going to belabor all of that this morning. But basically, measures of the fluence, the thing you can measure at the surface, just the photon density basically, and the underlying optical properties, if they're really small compared to their baseline values, which is generally the case in what we're looking at, you can model the photon density in this way and the change in optical properties in this way. It's called the Rytov approximation. And that allows us to get differential measurements where we're going to have, again, the change in light level is logarithmically, you want to relate it to the logarithmic difference of the time trace versus some baseline. And what we're going to use for the baseline is the temporal average. Why are we going to use the temporal average? We're going to use the temporal average because we're measuring hemodynamics. Hemodynamics in your brain, ideally, are not pooling and getting much higher absorption within a place, unless you are having a stroke right now, which hopefully you're not, or blood is like flowing out of your head. Generally, blood volume anywhere in your head goes up and down and up and down and up and down, but is remarkably flat over very long periods of time, or even very short periods of time. So we're going to use that as our baseline. At the end of the day, the denominator always matters in life, right? Like it's 3 what? 3 meters, 3 light years, whatever. The denominator is just like a unit. So in this case, we're looking at differential changes, and that is related to, again, as Joe said yesterday, the multiplication of the Green's function for the source, the spatial profile of where those photons go from that source, times the Green's function for the detector, same thing, but backwards in time, and then you normalize by the value of the source calculated at the detector to kind of keep everything well maintained. And again, that leads to this kind of spatial profile you have up here. So then, because we're doing this in a computer and not on pen and paper, you can discretize all of this in terms of voxels or in terms of a mesh space in the volume. And you can do this for many, many, many measurements all in parallel. And you get kind of a formulation like this in MATLAB with just series of numbers. But if you're not like, Neo from The Matrix, just to reference something that's 30 years old for some reason, we can put all this into a linear model to look at our favorite equation, y equals ax, where again, y are our measurements on the surface calculated at the boundary. X are our internal perturbations in absorption within the volume. And now A is our model, our transfer function. That really involves 3 primarily important things. The shape of the volume. Back in the day, it was semi-infinite, and then it was a sphere, and then it was a hemisphere, and now it's a head. And it turned out that the closer to the reality that you have the shape, the better your image reconstruction will be. Your internal distribution of optical properties, and the locations of the sources and detectors. So in NeuroDOT, as I said, we can use Monte Carlo outputs as well, but our preferred mode of dealing with this is to run Hamadani's NearFast, which is now called NearFaster, which is now also called NearFaster Too Fast, Too Furious, because they just wrote a new paper and that's what they wanted to call it. But basically, this has gone from when I joined Joe's lab as a postdoc in 2009, it would take like a weekend to run one of these models for a dozen sources and a dozen detectors, whereas now you could run it for 100 sources and 100 detectors in literally like 30 seconds on your laptop computer. It's amazing the advancements that these guys have been able to make. So then, the kind of primary focus of this morning's conversation, which again, it's a conversation, so if you have questions, please ask me, other than when can we go to Canada? You have y equals ax, and you want to get down to x equals inverted a times y. So there's a bunch of linear algebra. You end up being able to use this thing called the Moore-Penrose generalized inverse. It's super standard. And it involves this lambda term, the Tikhonov regularization parameter. And this term, we also call it lambda 1, controls the relationship between image, noise, and resolution but also smoothness. So if you have lambda 1 being a large value, you get big, blobby, beautiful images. And you're like, look how smooth my data is. That's great. But also, like, how much do I trust where everything is in terms of its spatial localizability? It's just kind of smooth. So then you turn lambda 1 down because you want to go after high resolution data. You're really excited about it. And then you're not quite sure which blob is the real blob because there's a lot of high spatial frequency information in your data. So there's a process to go through to kind of like tune this for a given imaging system. Again, that's the image variance penalty. As discussed yesterday, you can do all of this for 2 wavelengths. This is an example of 750 and 850. Nowadays, we use 685 and 830. But ideally, you have at least one wavelength on this side of this crossover isospectic point and another wavelength on the other side so that the light levels go up and down differentially relative to the absorbers that matter. There are many other absorbers in your head, like water, like lipids, etc. Tom is in your head, yes? I can comment on how you tune that lambda. So the question was, how do you tune the lambda parameter? I was going to put slides on that in here, and then I thought that would be slightly advanced. So I'll just say in words, there are 2 primary ways that we do. One way that we do is if you have another imaging modality that you trust, like fMRI or something, and you just care about the spatial map of the activation or of the pattern you have, you can take data from Joy in an MRI machine. You can then take data from Joy in your high-density DOT system, and then you can say, all right, I figure her data while she's tapping her fingers should look like the MRI data when I reconstruct the DOT data. So let's reconstruct it, bless you, but then tune this parameter a whole bunch of times and kind of find the optimal match. That's one way of doing it. If you don't have an fMRI machine, which I just got back from Italy, and a lot of people there are like, you can't just run fMRI, what are you doing? So then you can simulate it. You can get a nice image of Joy's head, and you can get an image of where all the optodes are, et cetera. And you can kind of run simulations, which we'll talk about in a little bit, where you basically imagine with X, again, is the spatial distribution of perturbations. You add a perturbation in a location, propagate it through A to simulate a bunch of measurements. You then run through this machinery to get A inverse to then recalculate what your simulated X reconstruction is. Do that for a whole bunch of different lambda values and you find a happy medium. That again kind of finds the knee point between image resolution and blurriness, as well as localization error and other parameters. And you can do what's called L-curve analysis to kind of like find the happy point in the parameters that you care about and then use those in the real case. The trick with doing that is you have to include noise in your model. If you never include noise in your model, you're going to be lying to yourself and your friends about how great your imaging system will be. So it's really important to characterize the noise of your system, which is like a whole other lecture that I'm not going to go through. But to characterize the noise in your system to then include that in your model, then those noise-based models do a remarkably good job of helping you kind of use L-curve analysis to tune these parameters. Good question. Yes, Tom?
Could you use phantoms to do something similar?
You could use phantoms if you had, oh my God, what's his name? I can't remember his name. Oh my gosh. So there's a couple of companies that make really, really, really nice phantoms now that also make dynamic phantoms as well. So you can get phantoms from them. And yes, absolutely use those. A challenge with phantoms, there are kind of multiple sources of noise. There's system noise and there's physiological noise. And system noise is important, and it's really great to model, especially as you go further and further out in your source detector distance where your light level gets really small. But the primary source of noise variability for us is like physiological noise. And so you want to bake that into your image reconstruction, even if you have phantom data as well. But yes, you can use phantoms. We need to make a phantom of Joy's head then to move forward with this conversation. All right, so anyway, functional near-infrared spectroscopy. You take a source, you take a detector, you multiply the Green's functions together, and you sample the brain. Wait a minute, no, you don't. You sample the superficial tissue because NIRS is very, very, very weighted to the superficial tissues. So what you do is you move your source detector pair further apart, and that's really cool. But now you have what we call partial volume effect, meaning that the time course of the signal represents changes in the absorption and hemodynamics everywhere along this photon path. So ideally, you want to be able to isolate data right in the middle of those optodes, which I argue is not a very safe assumption often, because again, hemodynamics everywhere along that path are going to contribute to that signal. But functional near-infrared spectroscopy, when the brain thinks, it changes color dynamically. Near-infrared, we detect the blushing of the brain with near-infrared light, and multiple wavelengths recover multiple absorbers, oxy, deoxy, and total. I meant to finish saying, before Tom asked this question, while there are other absorbers in the head, cytochrome is one that people are excited about, but also like fat and water, those don't change much while you're tapping your fingers or thinking about your grandmother. So you can kind of ignore them, and these are the ones that we really focus on a lot. If you want to go after cytochrome, good luck, and we can talk about it. Maybe it works. So anyway, building the head model, what we did back in 2012 is we got a T1 weighted MRI and a T2 weighted MRI. T1 is weighted towards fat content, and T2 is weighted towards water content. You can combine them together to segment the head into scalp, skull, CSF, gray matter, and white matter, which all have unique and differentiable optical properties that you can look up from other labs. Generate a computational finite element mesh. These are kind of the happy place for computational models to be solved remarkably efficiently for partial differential equations. Put the grid on the head, and with that, you've made your head model, you run your light model, again, through near-fast or through Monte Carlo, reconstruct your data, reconstruct your sensitivity, and then you can look at it both in the volume and on the surface. So this is kind of the basic mechanics of this. We developed about 13 years ago and haven't really adjusted much other than making things more computationally efficient. I'm going to really push on dynamic range here in a minute because I think this is one of the central most important things for getting really good image quality. Standard early sparse systems looked like this, where you had 3 centimeter separations. Then Joe came along and said, hey, why don't we push those closer together so we get access not only to these first nearest neighbor separations, but also these second nearest neighbor separations that are able to get more brain tissue, third nearest neighbors that are even further away, fourth and fifth nearest neighbors all together give us really good imaging at the level of the cortex. But that provides extraordinary challenges for the optoelectronics as well as for the coupling in dynamic range, as was discussed yesterday, over 6 or 7 orders of magnitude for the detectors. Also you need signal to noise above the noise floor of about a factor of 100 because individual changes in brain function are like these small little ripples on the water in the middle of the ocean where there's all of this crazy stuff happening all the time. And so we try to filter out those big waves with filtering and signal regression, et cetera. But at the end of the day, with fMRI and with optical methods, the changes you're looking at are generally like really small percentages. And so if you don't have good SNR above your noise floor, you're not going to be able to see all the cool stuff you're going after. So dynamic range, as well as minimal crosstalk, as was also talked about yesterday. It's cool if this detector gets data from everything, but it's very uncool if it's not able to like separate all of those different sources of variability and be able to actually reconstruct kind of independent measurement channels, at least in terms of data and light level across all of this. Then the third major challenge is optical coupling at the scalp through the hair so that we can get data also on you or on Milena, wherever she is, as was mentioned yesterday. So the pipeline for model generation kind of follows this up here, as I just mentioned. Again, we have y equals ax, where we're just trying to optimize a so that our estimation of x is as close as possible. A is the sensitivity matrix, or the Jacobian, as it's also called. It's a model that relates differential changes in light measurements to differential changes in internal optical properties. We like, when we finish making the A matrix, to visualize its sensitivity by calculating a flat field reconstruction. That is kind of shown here in example. This is shown over, I think, 4 orders of magnitude, which is a wild overestimation of where your sensitivity really is. It's really more in this kind of like red and yellow section here. And we'll talk more about that in a moment. So what's needed to create A? Again, the anatomical head model. From the volume, you get a finite element mesh with the optical properties. You put the sources and detectors on the head, as I'll explain in a moment. And then, again, multiple wavelengths to recover the spectroscopy. So the overall pipeline is I'm walking through this in such detail because you're going to do this in the hands-on section, I believe. Yep. So here's an example of an MNI segmented MRI. No, this is Ari's head, right? Because he has no face. If you want to see his face, he's right over there. And so Abby McGee, a super bright grad student in my lab that just defended her Ph.D., and others in the lab developed this Align Me app, which allows you to kind of fine-tune or gross-tune the optical imaging array on the back of the head, even if you have like Pohemus measurements, electromagnetic localizer measurements, or photometric measurements, et cetera, and you feel really confident for where your array is on a given tissue. This app provides a really nice opportunity to just kind of fine-tune where it is to then run your light model. And I and Ari will walk through that in a little bit. Calculate your sensitivity, again, with NearFaster. And one of the outputs that we look at is that GSD denominator that I was talking about before, because it provides a really excellent simulated light fall-off curve. Hello. Yes, please, Zoom question.
Given that HBO, HBR, and HBT signals can be recovered, should one be prioritized over the others, or is it best practice to report all three?
Great question. So the question is, because we get oxydeoxine total hemoglobin, should we report all three of them all the time, or should we prioritize one? I think big picture, that depends on one's question. And if you're looking at possible differences in neurovascular coupling or changes due to vasculature or local environments, for example, in cases of stroke or altered hemodynamics, it's very, very compelling to look at all three. And even more, HBD, Ilias likes looking at oxy minus deoxy. But I think if what you care about is spatial distributions of brain function profile relative to watching movies or tapping your finger or whatever, that often oxy gets you the information that you need. Oxyhemoglobin generally has the highest signal to noise, so it's something that we as a lab have focused on more. But a lot of people in the field, for sure, really prefer oxy and deoxy, and sometimes total as well, but I think it just depends upon the question. As Joe mentioned yesterday, sometimes maps of total provide better resolution, and as he also mentioned, with the human imaging, sometimes it's true, sometimes it's not, but it has lower SNR than oxy. So again, I think it depends upon your question. So the GSD provides kind of a simulated light fall-off. Again, that's the value of the Green's functions at each source evaluated at each detector. And this is basically a noise-free simulation where, look at that, I have 10 to the minus 12 relative to the input light level of dynamic range. That's totally awesome, but that's not the way that it really works. So what you can do is you can use this to build simulations that also incorporate system and physiological variability in your light model. You can see where your system will plummet into the noise floor and use that for dialing in your regularization parameters. Last, we calculate the sensitivity with this flat field reconstruction. And again, NeuroDOT provides the tools and a framework to make all of this easy that you can walk through. Ari is going to go through more of this, so I'm not going to belabor all of this right now. You can load in the volume. You can set different parameters to make your computational mesh really high resolution or low resolution, et cetera. It all depends on what you're trying to optimize. This is an example of a pad file from a Lumos system that we have in the lab placed on the head model inside of Align Me. These are two Lumo system examples because we gave a Lumo workshop a month ago. But this also works with ISS and with NearX and with Artsinus and with Esper Image. We can basically take the source detector array for any company system and plop it on here and Align Me and build light models very efficiently and very quickly. Ari is going to walk through all of this. The basic idea is that you can use participant-specific models to place your array. You can also use Atlas optimized models. You could load a sphere if you really wanted to. You can scale the Atlas down to your participant or up to your participant. The more measures of your participant head size, if you're just taking their data with the NIRS but not with the fMRI, you can plop that in here and allow the atlas to scale to your participants so you can kind of get as good a light model as possible. Dialing in alignment can take just a few minutes, and it can take all day. It depends on what you're trying to do and the complexity of the grid and the anatomy as well. It's all by hand, but it's remarkably fast and efficient. It's one of those things where if you just like throw your gloves down and get busy doing it, it doesn't take very much time if you're willing to do it. We have this little panel over here so that if you took a bunch of photos during your data collection, you can load them in, cycle through them, rotate them around, and use them to help kind of place where your optoid array is as well. It looks like that. We then relax the optodes onto the back of the head, imagining that all the optodes are attached to their nearest neighbor friends on springs as well as attached to the head. And essentially the array kind of adiabatically relaxes onto the surface of the head. In some cases, if you have a very complex spatially distributed array, you want to break the array apart into different little panels and relax each of them separately before recombining them. I don't know if that's something that Ari is going to discuss or not, but it's something to just be mindful of. So we've used this type of formalism to deal with quite a wide variety of real and imagined cap designs. So if you have any questions about how to do any of this, please reach out to any member of our team. We're happy to walk you through it. So in the end, you get optodes sitting on the back of the head or the front of the head or wherever they happen to be. Once you do that, you run the light model through NearFaster, calculating the Green's functions, visualizing the sensitivity matrix, et cetera, as I walked through before. So we always look at individual source detector pairs in the volume to make sure that right is right and left is left and up is down, and et cetera. We've collaborated with a lot of people who are used to thinking about data as if you're looking at someone's face as opposed to the back of someone's head where everything is backwards, and that's fun. Joy knows what I'm talking about. And so standardization in fMRI was a thing, and then they sorted it out, and I think standardization in fNIRS was a thing, and many labs are working on sorting all of that now. And so that is kind of our convention, is that volumetrically the right-hand side is the right-hand side, as if you're looking at the back of the head and the top of the head, as opposed to the feet. That's just easier for my brain, so now it's easier for all of your brains too, sorry. But that's kind of what we're doing. So then, given all of that, image reconstruction, we're moving from up here from model-based down here to reconstruction. I know I feel like I'm going fast, so I don't know. Does anyone have any questions before I continue? In Zoom land or in room land? Hi, Dina.
Hi,
Good
Adam.
morning.
Does the workflow require both a T1 and T2 contrast, or will one or the other do?
Question is, does the workflow require both T1 and T2 contrasts, or does just one of them do? That's a great question. Back in the day, we needed both to get really good segmentation of scalp and skull and CSF, because either of these by themselves didn't always provide very differentiable information. Nowadays, either one generally works really, really well. You can also, if you don't have that, or if you have kind of a poor T1 or T2, but it gives you a really good shape, you can use that and then move an atlas to that participant volume and then use the internal optical properties of the atlas as a way to kind of get an estimation. Kind of the shape and the location of the optodes are the two most important things. The internal distribution of optical properties, because you're looking at differential measurements, can be a little bit wrong, and it's not a huge deal. If they're really wrong, then you're going to have a bad time. But generally speaking, if you have an estimate of the shape from either of these, or even a CT, for example, can work really well, that can get you going to reconstruct your data. Good question. Any other questions before I move on? Hello.
Are there any age-specific atlases, like for example, like newborns?
Oh, newborns. Now, see, you're asking hard questions. This is good. So the question is, can you use just any atlas, and what about like newborns or et cetera? And so I would say that we are trying to put together a growing library in NeuroDOT, but there are other resources beyond our toolbox to have atlases kind of across the lifespan, but also that cover different races and ethnicities to be able to get head sizes and shapes that match the participant. You don't want to scale the MNI atlas or one of our participants down to an infant because, our heads don't grow uniformly like spheres, There's skewing and elongating, et cetera. And so in the toolbox now, we have MNI atlases for adults, but then also I think 6, 12, 24 months, and then age of 6 years or so. And we're trying to find more, generally from MNI, but also from other atlas generator resources to be able to populate those for everyone. But at the end of the day, you want an anatomy or a shape, distribution of properties that as closely resembles your participant or patient or subject as possible. It's a great question. And it can be really challenging. Maybe Sungmin will talk tomorrow about taking data from very, very young kids at the bedside and figuring out how to get a good match to that anatomy based on available atlases can be a challenge that needs to be addressed. Good question. Other questions? No? Okay. Well then, continuing on. For the image reconstruction component, I'm going to lean on the data a little bit. So this is an example hearing words data set as we published 11 years or so ago. So the idea with this paradigm is that it starts with 30 seconds of silence. I'm not going to wait 30 seconds. But then 15 seconds where 1 word per second is kind of coming over a speaker, and then 15 seconds of nothing. That block 6 times. Why that? Because, as Joe said yesterday, we stand on the shoulders of other people that already knew what they were doing, so we followed Steve Peterson's 1988 Nature paper, and this was one of the key paradigms. It led to maps like this, averaging across 5 people. With fMRI, those same 5 people, not at the same time, as they did fMRI, did DOT, and we get pretty similar maps. So we're going to use an example of these data to talk about image reconstruction. This is an example, sorry about the thresholding, but this is an example not from the data from that system and that paper, but this is more recent data from one of our kind of whole head LUMO systems. Apologies to Ed. So the linear model, again, y equals ax. A is a sensitivity matrix, and there are actually 2 regularization parameters. First, lambda 1 that I mentioned before, tuning the balance between resolution and noise. If you have a large lambda 1, you get like larger reconstructions, and if you have a smaller lambda 1, you get smaller ones, but your images can get speckly. And then lambda 2 tunes the depth of the reconstruction, and I'll talk about that one a little bit more in a moment. Here's again the reconstruction pipeline that we talked about. When you're actually reconstructing, there are a couple of other parameters to keep in mind. In addition to regularization, you also want to keep track of your source detector separations, because if you go too far out and your imaging system doesn't have the dynamic range to support it, you're going to include a bunch of noise in your measurements, and you're going to use those measurements when you're inverting your A matrix. And it's really key to invert the A matrix only for those measurements that you're using in your reconstruction. It's very, very bad to invert your A matrix and then remove the measurements that you're not going to use. It does not work well at all. So the source detector separation of maximum utility depends very much on the dynamic range of your system and your light fall-off curves, et cetera. Then we're going to reconstruct in the image volume. Okay, so if we reconstruct hearing words data, we might get kind of a bilateral map that looks like this at this time point. This is a visualization that we use in NeuroDOT called plot slices time trace. It's one of my most favorite visualizations because it allows you to explore your data in all 4 dimensions, X, Y, Z, and time. This is an example of block average data where it's just 30 seconds long. We've already processed our data and reconstructed it here. You can click on any voxel or any time point, and it will move the other 3 to show you what's going on then and there. It's really awesome for data exploration. So typical values of lambda 1 for the vast majority of cases is 0.01 to 0.1, where 0.01 is more high spatial frequency noise, and 0.1 is a little bit more relaxed and smooth. Now lambda 2 is called spatially variant regularization. This was first used, I think, in one of Joe's papers from 2003, which then referenced a Brian Pogue paper in breast imaging. And the idea is that it increases the sensitivity in the deeper voxels, which effectively, as you tune it in, pushes your reconstruction a little bit deeper into the volume. Now, if you tune it too low, you explode your reconstruction. I didn't include an image of that, sorry. But the reconstruction just fails catastrophically. But this is a great parameter to dial in simulation and or in, again, subject-matched multimodality situation. But if you don't use spatially variant regularization, DOT reconstructions, especially for CW, are almost always too close to the surface. If you use frequency domain reconstructions where you have that extra phase information, you may not need to use as strong of a spatially variant regularization, which we showed with Hamid Degani in a paper a couple years ago. And so I'll talk about that more in a minute. So as you change lambda 1, you can see that there's more spatially kind of variable data. Everything gets a little bit smaller. If you change lambda 2, it's more subtle, but the data kind of just pushes a little bit deeper in the volume. So again, you dial all of these in with cross-modal comparisons. So lambda 1, again, there's a trade-off between smoothness and noise. Here's a small lambda 1 where things are a little bit small. Here's a big lambda 1 where you've just blurred everything out. And now the hearing words data is all across the hemisphere, so it's too much. So you kind of want to go back and forth until you find a happy place. This is 1, which is a huge value for lambda 1. Again, looking at lambda 2, you have to really change this parameter quite a lot for it to move a lot. If you make it very, very small, that's when the data kind of starts exploding. RSD max, again, if you use kind of the happy place, you get a good image reconstruction. If you move RSD max, the source detector separation, too close, then you're not really sampling the brain very much, and you're not going to get very good image reconstructions. These kind of still have decent reconstructions, but it's nowhere near as good as the longer data. And if you go too deep, you're going to include a lot of noise in your reconstruction, and it's hard to see in this view, but trust me, it's not as good. But we can play around with that more with RA and others. So then you can also look at absorption volumes. You can look at oxy, as we've been focusing on. You can also look at just changes in mu-A. Those are reconstructed volumetric data at either wavelength. You can look at oxy, deoxy, and total, which again, unless there's some weird change due to hemodynamic variability or neurovascular coupling, these maps are generally going to look very similar, with the exception that HBR is negative. So in response to hearing words, you see a strong positive in oxy with a negative in deoxy, and again, a positive but a slightly less large activation for total. But the main thing, again, in terms of like NeuroDOT and toolboxes, these are just tools you can use to explore your data as you play around with these different parameters. Spatial smoothing is kind of the last major thing. Whenever you invert your A matrix, oftentimes, regardless of your regularization parameters, there's just a little bit of speckly noise due to just the mathematics involved running on a computer. So we generally recommend at least some modest amount of smoothing of your inverted A matrix. You can also smooth it much more to try to recover the goodness of your data until the data gets fully blown out. But this is kind of the last major parameter within the pipeline for image reconstruction. All right, with all of that, we're going to transition to simulations for a few moments. This was a really nice paper by Brian White and Joe back in 2010, after they had the in vivo example in the 2007 paper. Brian ran some nice simulations showing the differences between the high density array as well as from a couple of commercially available systems like a square grid array or a triangular array. So the way this works is, again, this whole imaging domain is X. These measurements are all Y, and then they had an A matrix based on the optical properties and kind of the shape of their semi-infinite model here. And so you would have a point spread function that's generated by placing a perturbation in X right there. It's basically a 1 at that voxel and then zeros everywhere else, okay? You then propagate it through to simulate Y, propagate it back to simulate your reconstructed X, And this is what it looks like. It's not just a little dot, it's a spread function that has everything to do with the geometry of the grid, the tissue, and your regularization parameters. Same basic idea you use with microscopes, where you just have like little lines of different size and you look at it down at the bottom of the microscope, but now this is not super simple optics, it's diffuse optics, so this is now what it looks like. You see with a high density grid that there's good triangulation that allows for the point spread function to be relatively even, spherical. Whereas for the square and the triangular array, you see there are these weird kind of artifacts that show up. And so you can play this game at voxels everywhere along the field of view and make these really nice kind of like carpet plots, that represent metrics calculated on these point spread functions. So one common metric that we focused on a lot is localization error. Is the perturbation reconstructed in the same location as you placed it? And so what you see is for the high density array, the perturbation localization error, which, is the distance between the center of max of the point spread function and the location of the perturbation, is relatively smooth across the imaging domain. Whereas for the sparse square and the sparse triangular matrix, there's this kind of spatial bias where there's a geometry of the grid that's kind of implanted onto the reconstructed domain. And essentially what this shows is that your reconstruction, depending on where it is, or your perturbation, depending on where it is under your grid, is going to be kind of pushed or pulled over into certain kind of preferential areas. And what we want to do in imaging is have an even imaging domain as absolutely possible. Otherwise, all of our reconstructions are going to show up there, or there, or there, or there, or there. It's going to kind of suck it over. Similarly, for the triangular array, you're going to have kind of good imaging there, but really terrible imaging along here. Similarly, you can look at effective resolution, which is basically you have a point spread function that looks like this blue circle up here, blue oval, relative to a perturbation there. Your effective resolution is like if you draw a sphere, or a circle in this case, centered at your perturbation, but that completely contains your reconstruction. It gives you a sense of both your full width at half maximum, like how large is the point spread function, but also how much error is there and where it's placed. And so your effective resolution, again, is relatively flat within the high density grid, but there's all this crazy artifact in these sparse grids. So the whole game, I think, with high density arrays is to properly triangulate the spatial variability in your data. You can also extend this game to kind of spatially extended perturbations and look at differences in the actual shape of your reconstruction, and there are nice movies of these things moving around in this paper. You can then say, all right, well, that's neat, but those are simulations. What bearing does that have on real life? Certainly it couldn't be that bad. So we took one of our retinotopy data sets from around 2012 in the visual field. Who in the room has been in an MRI machine? Oh, awesome. Good work. All right. Who has done retinotopy? Oh, the rest of you are really missing out. Okay, so while you're here, sign up for a study with any member of my team or Joe's team, and we'll pay you money to sit in one of our caps, because it's really fun. It's you stare at a gray screen with a white cross while the flickering checkerboard, oh dear Lord, while the flickering checkerboard reverses at 8 hertz. It's really annoying, and it's hard to stare at this white cross while this is happening. But if you're able to do so, and you're in an MRI machine, you'll get a strong activation in contralateral visual cortex. These are models of the back of the brain. Left lower visual field flickering checkerboard, upper right visual quadrant activation. So one of our participants came in a week later, sat in our DOT system, and you see that this reconstruction looks kind of like the fMRI. But if we simply take the identical data and remove all of these other green lines and just show these green lines, we get all of this other nonsense. This is just from undersampling the variability that's in our data. It's the identical data, we just removed these measurements. Trying to make the point here that one strong aspect of the high-density DOT is that it is allowing you to triangulate the spatial variability within your data, so you can get more fMRI comparable image quality. Okay? All right, so a moment about frequency domain. With our friend Hamid, I visited him a few years ago, and we built one of these high-density visual pads in his lab using the ISS system. And so that allowed us to do frequency domain HDDOT of the same retinotopy data that's been like the bread and butter for the last 18 years or so. And so what we're looking at here are the power spectra, so the Fourier transform, now averaged over just the 13 millimeter data. And you see that at 10 to the 0, or about 1 hertz, we have a little bit of a pulse signal there in the intensity. If we move down, there's a little bit of respiration data. If we move further down, this is where the stimulus repetition frequency is, which is how often this thing kind of repeats going around in a circle, which is 1 over 36 seconds. And you see that there's maybe a tiny little bump there, but not very much. If we move now to the average of the 3 centimeter data, we see a little peak. If we look at the average of the third nearest neighbor data, now we're getting very, very clear sensitivity to that variability that we know is due to brain function and not due to superficial tissues. If you look at the fourth nearest neighbor, the signal to noise starts going down, so that signal starts going away. But now, if we look at the identical measurements, but rather than looking at the intensity, we're just looking at the phase. You can see that the first nearest neighbor data has this totally strong signal that we know, again, is brain specific. So something about the phase aspect of the data is actually sampling deeper than just the intensity signal coming out of the ISS system or out of any frequency domain system. And so this is hinting again that the phase provides a deeper sensitivity profile and therefore an opportunity to measure just a little bit deeper into the head if you can get the signal to noise to work out. So this made us really excited, and we published a couple papers in SPIE and neurophotonics showing that if you can get good SNR with a frequency domain system, you actually don't need spatially variant regularization. So this is CW without the spatially variant regularization and FD also without it. You can get somewhat deeper reconstructions. And so we ran a bunch of simulations to try to understand what was going on. And these are just examples of the kind of banana sensitivity for intensity and for phase, just again showing that the phase bananas run a little bit deeper. And so we ran a kind of extensive set of simulations where we had human-specific head models as well as human-based noise models of the data. And we put perturbations just on the edge of the brain and then a little bit deeper in the brain and a little bit deeper in the brain again to see how well the frequency domain would compare against the CW approach. So I'm going to go through this step by step. So this is an example of a simulation about 13 millimeters below the surface. On the top row is the CW reconstruction. On the next row is the frequency domain reconstruction. But now for each column, I'm highlighting the effect of dynamic range. If you have dynamic range that's able to get just the first 2 nearest neighbor pairs, your reconstruction is a little bit superficial. And again, this is without spatially variant regularization. But the FD is able to get that reconstruction kind of within the full width at half max. But as we add more dynamic range into our system, including further and further out measurement pairs, you see that CW actually does a really great job when it has the dynamic range to support it, and the FD keeps getting better. Now, if we go a little bit deeper, 17 millimeters below the surface, you see the CW starts having a hard time if you have limited dynamic range, but as you have more dynamic range, the CW is still kind of able to get it in the full width at half max, but the frequency domain case with the dynamic range is able to reconstruct the data pretty well. If we now go even deeper, 22 millimeters below the surface, which is pretty ambitious for optical imaging, you see that the CW really needs all the way out to almost 50 millimeters dynamic range and is still not quite accurately localizing that spatial variability. With the FD system, you can actually spatially localize the activation, but you require this very large amount of dynamic range, which can be really challenging for a lot of these commercial systems. So with Hamid and Matthias and this empirical noise model, we showed that the addition of phase leads to deeper high-fidelity imaging than just CW, and more dynamic range provides more distances, more overlapping measurements, and better image quality deeper out. So we ran models without noise, where again, you think that the world is a wonderful, beautiful place, and then you add noise and you realize how hard life is. But it gives you a nice target to go after in future advancements in system design. More recently, my grad student, Weiyao Fan, who just defended his Ph.D. last December, ran a updated set of simulations looking at different modulation frequencies, both with and without noise, to try to see that if one were going to try to advance frequency domain, are there frequencies that we would want to target? And so these are just examples of line profiles through the sensitivity profile here. These are A matrix bananas in intensity and in phase, showing that the depth of modulation gets a lot stronger as you increase the modulation frequency. Very long story short, just to keep it brief, using an empirical frequency-dependent noise model, we show that higher modulation frequencies improve imaging in the noise-free cases. So this is an example of the localization depth where you get really good imaging, just kind of plateaus for a minute and then keeps going up if there's no noise in your model. And as you have more dynamic range with the NN4 from the NN3 system, you can see you can image deeper and deeper and deeper, and that's really exciting. But if you have a realistic noise model, you see that the noise at very high modulation frequency actually turns over the curve of good image quality. And so rather than thinking that you can image more than an inch into tissue, almost 3 centimeters, you see that really we can barely get past 2 centimeters from the surface, even with really good dynamic range. But this does provide a target of about 300 megahertz to see if we can build updated electronics or work with our friends at the companies to update electronics, because maybe a higher modulation frequency would provide access to deeper tissue variability. Okay. Any questions? The current standard is 141 megahertz, if I'm, no? Or the default standard is 141, yeah.
We picked that 141 as a default because the system has a lot of frequencies in it, and you have to find special frequencies that work to give stable phase for electronics reasons. But of all the frequencies we could pick, that one had, I think, about 1 or 2 dB roll off in the modulation depth. So beyond that, with this current instrument, the depth of modulation goes down, which would essentially have more noise.
Mm-hmm.
So you can set that machine to 250.
Yes.
But it won't have a very good depth of modulation. So it wouldn't maybe prove your theory because you get so much noise.
Yeah.
But we could work on trying to get that depth of modulation higher at 250. But we picked that default just because the electronics we were using worked up to that speed.
Yeah. So this is Dennis from ISS. So anyone that wants a frequency domain system, talk to Dennis. They're totally great. We had one during the demo that Aaron was manning yesterday. Other questions before we transition to the last section? Hi, Tom.
So to follow up on that, where did your noise model come from if it wasn't?
So that noise model was a combination of noise as a function of source detector separation developed with our CW system that was then extrapolated to a frequency domain by using the Applewhite? I'm blanking. Darren Robler's paper.
Applegate, yeah.
Applegate, thank you. Darren Robler did a really nice paper looking at different noise models for a frequency domain using network analyzers and using another approach as well that I'm also blanking on. But we basically used his kind of best case noise model to provide an optimistic target of where to go in the future.
So the take home is it's really dependent on the noise model.
Massively dependent upon the noise model.
Yeah.
And I think the noise model will come down, as Dennis is saying, as potentially as we improve electronics, we can improve the noise model further up into the modulation frequency space. Or looking at multiple modulation frequencies as you're doing, there may be other opportunities to improve imaging as well for brain imaging.
Yeah, we'll talk.
Okay, we'll discuss. Okay. All right, so how do we know that all of this nonsense is working in the first... Oh, do we have a question? Yeah,
hello.
please, yes.
So I have recently read an interesting paper from the University of Glasgow. So they actually claim that they placed the source in one side of the head, and they detected it on the other side of the head.
Yep.
So they could detect technically maybe a little bit photons. I'm not sure how much, but they could detect photons throughout the head. So is this even possible using Monte Carlo simulation? They said like they increased the power of the LED to detect 1 or 2 photons from throughout the head. So I just want to know about your opinion.
Yeah, so great question. So our friends in Glasgow put a really bright source over here and basically put a detector over here that was sensitive, and they waited, right?
Yeah.
So as Joe talked about yesterday in terms of source encoding patterns, if you're trying to take brain function data that's super meaningful, you want to take data at 10 hertz or faster, but not much slower as kind of a benchmark. And that provides, or that enforces, that demands really stringent criteria on what your actual noise floor is going to be. Because if you're trying to collect data at 10 hertz, you're not going to get a lot of photons sitting out the other side above your noise floor. But, and this was shown a few years ago by the Polish group, also out of Adam Eggebrecht's group, that if you have really big detectors and you wait a while, you're able to lower the noise floor for your measurement, that sure, you can get photons. But like, I don't know, what's the signal going to tell you, right? Because those photons are going to have sampled so much of the brain that it will be challenging to localize any variability, no matter, I think, how complex the experimental paradigm might be to kind of try to isolate thalamus or other things. So you can certainly play a lot of games to like shine light on one side of the head and detect light on the other side of the head. How to then incorporate that into, you know, diffuse optical functional brain imaging is another question.
Got it. Thank you.
There's like Bruce Stromberg used to, maybe he still does, when he gives talks, start his talks with like having a super bright halogen lamp inside of his mouth, and you could see part of his head glowing. So like, sure, you can get photons through, but what does it tell you at the end of the day?
So it is not actually practical, right?
I'll be conservative and say it depends on your question.
Okay. Thank you.
You know, yeah. I mean, one person's completely insane, wild idea might be totally perfect for someone else's application. You know, yeah. I think having a big tent and all that will keep our minds and doors open for like bridging across the field to like try something nuts and new that might actually open the door to something that someone else would have thought would never actually work. You know. So, any other questions before we turn to the last chapter of this morning's conversation? No? All right. So, some of this was already discussed yesterday morning, but I just wanted to revisit it within the greater context of what we were talking about just recently. So, a benchmark for functional neuroimaging techniques, first with PET, then with fMRI, and then with DOT, was doing retinotopy. Again, as Joe mentioned, you can stare at a white cross, and there's these annuli that kind of flicker and move out, or that move around in a circle, and many, many groups use this to map out, you know, medial visual cortex and other areas of visual cortex. So this is data from our 2012 paper, where we showed that the accuracy could be within about 5 millimeters on average within the area of the visual cortex that had high sensitivity. Excuse me. And this spatial agreement was all driven by the head modeling approaches, excuse me, given that the fMRI data was not collected at the same time. You can look in this data more deeply by placing a region of interest in visual cortex, and you can see these kind of sinusoidal-like time traces. Red is oxy, blue is deoxy, green is total hemoglobin, and black is the bold signal, where you have really good agreement here just because, again, the head model aligned the DOT data with the fMRI data. You can calculate the Fourier transform of this, and you get something like this after massively bandpass filtering your data. And if you look at the stimulation frequency here, here's the magnitude, and if you calculate the phase, that basically provides a transform between a phase in time with a phase in space. And so following Marty Serino and other people's work in fMRI, we drew these rainbow maps on the back of the head, and again, you can see that for when the flickering checkerboard is down here, you get a strong activation up here. When it's over here, you get an activation over here, and that there's really good agreement between DOT and fMRI. And more recently, Wei Hao Fan in my lab and Zach Marco in Joe's lab in simulation and in reality showed that higher density systems are able to achieve higher spatial resolution. And as we think that as you keep squeezing these closer and closer and closer together, you're even able to get the effective resolution below a centimeter or so. But then, of course, that brings up a lot of other challenges in ergonomics and getting everything to actually fit on someone's head without shaving their head, and while keeping it, something comfortable that people would like to do. So, walking back in time, we then extended the system from the visual cap out to the 96 by 92 cap, and went and talked to Steve Peterson and Brad Slager and Avi Snyder, who said, again, to repeat this PET study, which was the first time kind of the hierarchical nature of language processing was demonstrated in the literature. Steve got very famous partially because of this paper and other things. So in response to hearing words, as I showed you before, you get bilateral auditory cortex. In response to reading words silently, still 1 word per second, 15 seconds on, 15 seconds off, just 6 blocks, just 5 subjects. You get a nice activation in visual cortex. If you imagine speaking each of those words and then subtract from that map this map, that gets rid of the visual but keeps the motor mouth part of cortex. Even though you're not moving your head, you're just thinking about saying a word out loud, part of your brain becomes active that you can visualize with optical imaging. Then for each noun on the screen, if instead you ask people to say an associated verb, like if the verb, or if the noun is dog, you might think bark or kick or something, and then that turns on left lateralized dorsolateral prefrontal cortex. Again, subtracting from this map. And the important thing is then that all recapitulates what we saw with fMRI with good overlap between the two. I want to really highlight that this wider field of view not only is able to see the things that we expected to see, but it carries along with it control regions that are not turning on when they're not supposed to turn on. So having a wide field of view kind of gives you positive and negative controls for your experimental paradigm, allowing you to have greater confidence in the data that you're collecting. We extended this through COVID, kind of data before COVID, published after COVID. Mariel Schrader and others in the lab went and got 30 adults because we were curious about overt verb production, because we wanted to extend this to conversational experimental paradigms in kids developing autism or not developing autism. And we wanted to see if our systems would be able to give us good image quality even while people were talking. And so this is just the data from those 30 people while they're covertly reading words, but without any thresholding, so you can kind of see more of the kind of the bell of the language system ringing while people are reading, or covert verb generation, which is very similar to what I showed you earlier, but now this is without subtracting this map. And then overt verb generation is very similar. We get good data quality with, in addition, like motor mouth and auditory cortex. So here's all of those labels. If you now do the contrast, you see that covert verb generation gives you the map very similar to what I showed you before. Hello.
Any suggestion of software toolboxes to examine the association between HDDOT data and behavioral data?
Software toolboxes to look at the relationships between DOT data and behavioral data? You could use NeuroDOT. You could use, so I mean, at that point, I guess I would say you could use any of the fMRI-based toolboxes, because kind of the reason for existence of NeuroDOT is to A, visualize data everywhere along the processing stream, but also to be able to reconstruct data into a volumetric space so that it's basically a nifty format, just like fMRI does. And then you can do with the data what you wish. And so the fMRI community is far more mature than ours. And I'm certainly not a statistics expert to the extent that people that develop these toolboxes are. So once it's in nifty format, you can use the whole set of tools that have already been built, like SPM or FSL. You can run things through R, et cetera, to build and run regression models that compare behavior or a group, et cetera, to reconstructed DOT data. Good question. And so if we look at, just to highlight here, so then overt versus covert, the only real strong differences are in motor cortex because people are moving, and in auditory cortex, which gave us a lot of confidence that we can go and apply these tools and methods to do those types of studies. Here are statistical parametric mapping based regions. Again, we had it recalculate the DOT autocorrelation both in time and space rather than using the fMRI kind of built-ins. And these are time traces at each of these regions of interest, showing that in some regions, like in visual cortex, the responses after doing finite infinite block averaging, impulse response block averaging, that the responses look very similar, but in other regions of interest, the responses are highly idiosyncratic depending on what the task would be, as you would think. So just to highlight that we are able to get the signal to noise to kind of differentiate these types of activity at different places around the field of view. Samira Malega Hassanpour with Jonathan Peel. Samira was a grad student in Joe Cover's lab, and Joe obviously. Also extended all of this to looking at syntactic complexity, auditory cortex for listening to noise, easy sentences where the object or where the subject is the beginning of the sentence. You can see the activation in the head just listening to this. Listening to hard sentences, women that men assist are helpful, give you a similar thing, but looking at the contrast of hard versus easy, you are able to interrogate higher order areas of language and attention and control regions in prefrontal cortex. Last, I'm going to highlight functional connectivity. This is based on functional fMRI, where you have a region of interest in posterior cingulate cortex as a time trace kind of like this. If you look at a functionally related region, even though it's very far from it, like medial prefrontal cortex, you get very similar time traces, even though they're clearly not in the same vascular beds. Whereas if you place a region of interest in a functionally distinct region, here, inferior parietal sulcus, you get very different time traces. And so you can make maps of the temporal correlation within the field of view. You can, with fMRI, you can move your ROI kind of all throughout the different cortical places and look at the functional network switch and change and come up, and it's really beautiful with data from the Human Connectome Project, et cetera. But then, you can do the same thing with optical neuroimaging data and recapitulate all of these resting state networks that have been, again, kind of bread and butter for fMRI for the last almost 30 years now. And you can also use these parcellation-based approaches with DOT, as maybe talked about later. So again, as Joe mentioned yesterday, with this extended field of view, we were able to show not only bilateral correlations, but also anterior-posterior constellations of regions as is indicative of these kind of cognitive networks, including the default mode network, which is associated with, 5 minutes, okay, thank you, which is associated with daydreaming, as most of you are probably doing now, or self-referential episodic thought, et cetera. So the default mode network is implicated in all sorts of things, and even though the medial nodes are kind of the most common popular ones for posterior cingulate, anterior cingulate, there are these lateral nodes of default mode which could be super compelling for looking at in terms of autism or language development or any number of other things. So back in 2014, we also used the resting state maps to interrogate the resolution by basically moving our region of interest from back here just a little bit forward to move from visual network up into dorsal attention network by seeding area MT, and seeing that there's this kind of transition phase where this is the spatial correlation of map 1, map 2, map 3, all to each other. And you see that the DOT kind of topography moves to this transition over a similar range or border size as the fMRI data, again, with the same people in the same locations, et cetera. So in terms of using the resting state to kind of validate what we're actually able to get out of our system, there are kind of many approaches you can use with the same data. Last thing here is focusing on baby data. This is all data kind of collapsed across a few studies with Steve Liao out of Joe's lab, as well as Brian White and Savina Faridol. This is her latter paper looking at a larger field of view on a baby cap, looking again in real-time assessment of coupling coefficients and measurements that survive, building a light model for the baby and similar approaches as I walked you through for adults. The DOT system at the time was able to show single subject signal to noise, where you see bilateral connectivity in term and preterm kids and a kid with a stroke, again, as Joe talked about yesterday. I wanted to take a moment and kind of linger on this slide as well, as this shows a similarity between the DOT and the fMRI. This is in, I think, 11 kids, where again, the DOT and the MRI is not collected at the same time. But over this limited field of view, you can see that the spatial correlation, or that the spatial maps of correlation follow each other in a way that is also specific to the functional network. And it's been shown in humans and in animal models that visual cortex has higher correlation very early in life than higher cognitive networks or than auditory networks. So it's nice to see the optical system is able to show developmentally sensitive signals that could be very informative for the type of study that you want to undertake. So again, there's the full pipeline for optical brain mapping, as will be walked through in the hands-on sections today. Sections on pre-processing, the log mean, detecting noisy channels, filtering, superficial signal regression, which is profoundly important, et cetera. The head modeling, where again, you can use any number of tools. FreeSurfer is kind of our favorite. We have built-ins if you don't have access to FreeSurfer or don't want to wait the 8 hours for it to run. Head model generation, where you can use NearFaster, Seagal, ISO2MS out of Ching Fang. Intuitive and interactive cap placement that again goes along with any of these other more automated tools. Light modeling with NearFaster or with Monte Carlo. Regularized reconstruction, all to get the target maps of brain function at the end of the day. So hopefully you guys have built some deeper understanding of the conceptual steps involved, various strategies for modeling, and been able to explore some strategies for simulation and functional reference validation. And with all of that, thank you for your time. Do you have any questions before we take a photo?
Thank you for your talk. It was amazing. Do you always use a fixed differential path length factor for all of the subjects?
That's a great question. So the path length factor is something that you have to kind of like make up if you're doing modified Beer-Lambert law analysis or individual measurement analysis. Some people use numbers between 1 and 6, for example. But if you run through the light modeling in the NearFaster or Monte Carlo approach, it effectively calculates those through the Green's functions. So you don't ever have to set the path length factor if you do the image reconstruction based on the Green's functions and the inversion of the A matrix.
Thank you.
Good question. Other questions?
You mentioned that one way of determining the regularization parameter would be to compare an fMRI task with the HDDOT. Would that be the same regularization parameter if you were to determine it by comparing finger tapping and then use the same regularization parameter for a retinotopy?
Yeah, absolutely. Yeah. So if you have a really wide field of view system, as you're implying, it's definitely good to focus on that localization error parameter, not only where you're wanting to look, but also just tracking kind of what else is happening across your field of view. When we're rerunning things now, if we build a new system and say, all right, well, let's see if the regularization needs to change, we typically do visual and motor and auditory, and just like make sure that if you tune in one, you don't go and ruin all of the others. So you're kind of finding the happy medium. But typically, once you fix it one place, it works everywhere.
Thank you.
Yeah, good question. Question from Zoomland.
Indeed. Can HDDOT accurately map the DMN despite its partial inaccessibility to deeper structures?
Can, yes. Right? So can high-density DOT partially match the default mode network? So a challenge with a lot of these resting state networks is they're exquisitely sensitive to spatial localization of where your region of interest is. So you could try to run ICA to have more of a database, data-driven approach, or use parcels to like improve your spatial sampling of your data. Some of these nodes or the kind of cortical representations of these resting state networks are in the sulcus. And so depending on who your participant is, sometimes you have amazing signal to noise and you have a great map. And then on someone else, you have terrible signal to noise. And it's just a little bit too deep to be able to get really, really well. So resting state is one of those kind of challenging cases where sometimes it works and sometimes it's a little bit more rough. Any final questions before photo time? Yes, all right, one last question. But I'm around all day if you want to talk.
Thank you for your presentation. As we are doing almost the same thing, but we are in the animal stage phase, do you have any like anatomy of animal brain that you use, that atlas when you were in animal phase on mice or rats? So we get the connectivity, but we don't know that's how to validate where to put the seed. Is it on motor cortex, sensory, something like that?
What kind of animal are you studying?
Mice.
Nice. So my dear friend and colleague Adam Bauer down the hallway, also Joe, do a lot of mouse studies with the optical imaging, and the mouse movie I showed earlier is from their work. And so with them, I think with mice there is a wide library of, and a growing library of atlas information from the Allen Brain Atlas of various approaches, and Adam's published a couple of really nice papers, as probably Joe has too, on relating the optical brain mapping data to other atlas-based models, like Paxinos atlas for mice also can work to kind of isolate motor from parietal, from visual cortex, et cetera. So there are other atlases out there, but I would strongly recommend reaching out to Joe or Adam Bauer about that information. All right, let's take a break, take a photo, get some coffee. Thank you all again.